Good afternoon, everyone. My name is Ryan Hulguin with Arm, and today I'll be going over actually just debugging with DDT for this workshop. Um, I hope everyone out there is doing okay despite the current conditions. The agenda for today's talk is just going to go over the Arm software package, specifically debugging with DDT, and then I'll cover some specific settings that you need to know for debugging on the Theta machine at Argonne. So at Arm, we have this software called Arm Forge. It consists of both the debugger, DDT, and also the profiler, Map. One thing that's nice about Forge is that it supports all of the major HPC architectures. So the training that you're going to get today while debugging on the Theta machine, it's also still useful if you've managed to move on to a different type of resource, either hosted by Argonne or at a different site. So that's useful for you to debug no matter what machine that you might be running on. And we've made DDT in particular really easy to use. So most of the times that you can get information either by using your mouse and hovering over a variable, or just right-clicking to get some simple context menus that you can quickly scroll through. It's fairly intuitive as to how to use it. And also our software is highly scalable. So whether you're debugging locally on your laptop or you've got a supercomputer using over thousands of MPI ranks, DDT is still able for you to be used without bogging you down, despite how small or how large your job is. There are two modes that DDT itself can be run in. It can be run in on the right, what's called using the GUI with the graphical user interface. So you would use DDT-Connect, AP1 in particular for the Theta machine when you're running on there. And what that's going to do is that's going to connect back to your local machine, provided that you have the local client, which is free to use. That way you can debug fairly quickly with the graphical user interface. Alternatively, we have what's called offline mode, where that's useful if you can't be physically at your computer by the time your job runs, or you need to run it overnight, or it's a really long job. And what this will do, this is useful if you have a submission script. So you would just put this in your script, and what it will do is that for every breakpoint that you set, or if there's any crashes that show up, you'll get this nice little HTML output that you can scroll through at a later time to figure out what's going wrong with your code. Okay, so debugging with DDT, there are a few things that you need to do before you can start using DDT. Actually, let me take a step back. So DDT itself, it's a tool to debug your code, and with this tool, you're trying to answer a bunch of questions that might occur in your code. So if, say, for instance, one of your processes is not behaving the way you think it is, perhaps you need to scroll through the stack trace to figure out, first of all, how did it get to the current location where it is messing up, and figure out what values were being passed along the way, if there are function calls. DDT won't fix the problem for you. It's there to help you to figure out what is the current state. It's kind of like looking at a crime scene and just gathering all the evidence. One of the useful tools is what you see here on the right. This feature called sparklines. So you may have thousands of MPI ranks, and they all may have different values. So quickly at a glance, you can see what the value is for a current rank for this variable, say jcall, and you can see what the value is across all of the MPI ranks in your run. In this particular example, this was actually a prototype MPI library that was being debugged. And jcall was supposed to, actually, my PE was supposed to correlate to my rank. So what was expected was a diagonal line going from 0 to the number of ranks minus 1. But clearly you can see just from the spark line alone that the values are not consistent with what you would expect from my rank. So they were able to quickly see, just using the spark line, that there was a bug in their code. Okay, so how do you start using your code with DDT? So just as with any debugger, you want to enable the debug flags, typically with -G. And that's true for the Intel compilers that are on Theta. And we do recommend that you turn off all optimization flags when you're in a debugging session. Typically it's -O0. If you leave it out, it can cause the compiler itself to optimize out some variables that you might be interested in, or even some functions, making it difficult to debug. Okay. So one of the common cases of using DDT is if you have a seg fault in your code. So you see this, you see MPI run exits because there's signal 11, so there's some type of seg fault. And just from the terminal output alone, you don't get too much more information. But if you were to run it through DDT, as soon as that seg fault is hit, it takes you straight to the line of code where that seg fault takes place. So for this example, we can see that there's a segmentation fault at line 103. So you not only have it in text, you have it highlighted for you, and you also know the current local. Oh, sorry, I don't know why it's going on by its own. You also have the local variables that are in scope at that time. So you can use that to inspect the values. So for this particular instance, like I said, if you take the mouse and you just hover over the tab array, you can see that it was allocated with 13 elements. 13 by 13 array. And it's trying to access an X value that's greater than 4 million, right? So that's causing the segmentation faults. So quickly at a glance, you can see that there's something going on here. And it's up to you to figure out how these values got to be, how did this value get so huge to where it was invalid when it was trying to access this tab array. Other bugs in your code that you may encounter are not so straightforward. It may not be a crash, maybe something just, maybe values are off, or maybe sometimes it crashes and sometimes it doesn't. Most likely in that case, you've got some type of memory bug. And what you can do is you can use DDT to enable its memory debugging simply by checking this memory debugging option, and you can adjust the various levels of checks that you want done on the heap just by moving the slider. So by default, it's going to be set on balanced, and balance is a good mix of tests that tests whether that checks for some memory errors. And you can see here, this is as you go from left to right, from fast bounce to thorough, you enable more of these checks in your code that happen for you. You don't have to code up anything; it'll do this for you. But typically, balanced is what you'll want to use. Sometimes, if you use fast, it may not detect a memory issue in your code. And then thorough is really like your last resort if balance doesn't capture the memory issue that you're seeing. Also, I do want to mention that in addition to these heap debugging checks, you can also turn on what's called guard pages. Most people are familiar with the term electric fence. So that's essentially if you're touching memory outside of an array, more than it was allocated, DDT will stop you and tell you when that happens. So guard pages, also known as electric fences, it'll reserve memory space after your actual allocations in your code. And if for whatever reason your code touches this guard page when it shouldn't, DDT will alert you. But you do have to be careful when you use this feature, because every time you turn it on, it uses a lot more memory in addition to what you're currently using. So I know with the KNL, this can be kind of tricky, especially if you're doing it for every rank on all of the cores. So that's just something to keep in mind. So here we have an example. They've got a code. They ran it and it crashes. So they're looking at this and they see that the value is optimized out. So it's crashing in not their main code, but in actually Metis. And they see that this value is optimized out. And of course, they can't do anything about that because the compiler optimized it out. So they have to recompile the code with -0 in order to figure out what's going on. But once they did that, they can see that they've got this simple value. But when they multiply I times NT samples, they got a negative number, which you wouldn't expect. But the reason they got this was because of an integer overflow. So this was an instance where DDT was used to identify a bug that only existed at such a high MPI rank. DDT also incorporates version control. So oftentimes, if you're using version control and you have a bug that wasn't there before, it usually comes from the latest change. So you can actually look at what was changed, the latest change, and then just inspect those and see what could cause the problem there. Another feature that DDT has is this thing called a logbook. So you may be debugging your code and it may take you several hours, just looking through variables and going through, stepping in through functions, stepping in each line of code, and you may have to stop for the day, and you may have to pick it back up later. So what you can do is you can click on this logbook tab and then just save it. And you can also add your own personal annotations to give you an idea, to remind yourself what it is that you were actually doing when you had to stop for the day. And then when you pick it back up, you can always reopen the logbook. Okay, so at this point, I'd like to switch over to actually demonstrating the tool itself. I do have a interactive job already on Theta, so I just did a Q sub I. So the first demonstration, I'm going to compile. Notice that I've got -G for enabling the debug flags. And for this example, I'm also turning on memory debugging. So because Theta creates static executables, we have to manually link in the memory debugging libraries. And the way to do that is to add this compiler flag option. So it'll be in the slides that'll be available to you, so you can see how to enable that. Okay. Also in this directory, I have a submission script, even though I'm using an interactive session. So these are the commands that would be in the submission script had I submitted it through a script. But so I can just issue these commands manually in my interactive job. So I'm going to first load the Forge module. I'm also going to unload Darshan Exalt so I can get rid of some error messages that show up here using DDT. You don't have to do this, but it just makes life a little bit easier if you're using DDT. And then I'm going to do what's called a reverse connect connection. So on my local machine, I've already started up a remote client. I have already configured my local client. So you can see my configuration details. This is just my username at theta.alcfnal.gov. It's just going to point to soft debuggers DDT. And then when you do that, you're just going to start up a remote launch by selecting it from the drop-down menu, and then I'm going to type in my passcode. Just give me a second here. Okay, so this is my local client connecting to the Theta machine. As you can see at the bottom here, I am connected to Theta. So in my live interactive job, I can now run this job with DDT using the reverse connect command. And what that's going to do is that's going to notify my local client, hey, a DDT job is waiting for me, should I accept it? And then I'll say, go ahead and accept it. Okay, so for this particular example, I'm actually going to turn on memory debugging, and I'll turn off guard pages. And run. Oh, okay. So this is why you unload the Darshan module, because it actually wraps MPI init. The reason I still see it is because when I compiled it, it compiled into the static binary. But you can see from the stack view that MPI init actually is calling this Darshan function, which is fine. So the first thing I want to do is I want to add a breakpoint. So what a breakpoint is, that tells the debugger to stop at that line of code. And so as you can see, I quickly did that by just right-clicking in this area and then saying add breakpoint for all. Alternatively, I could have gone here to this breakpoint tab. I could have gone right-click, add a breakpoint. I could have given it a line number. I could give it a condition, say break only if a certain variable is a certain value. But here, a simple breakpoint is fine. So I'm going to say hit play. So as soon as the breakpoint was hit, I got this little pop-up and notifying me that all 4 ranks are at this line 106, which is the next actual C line of code that happens after the breakpoint. So I'm going to pause at this moment. You can see that the local variables that are in scope are argc and myRank. And for rank 0, myRank is 0. If I wanted to switch between ranks, say go to rank 2, just by clicking on it, you see how it updated automatically to rank 2, or to its value to 2. Okay, and I can go back and forth. Okay, so we can see from this for loop above that we have 2 arrays that have been created. One is a static array, so it's just a float with 12 elements each, and the other is a dynamic array. One cool feature of DDT is the view array feature. So I just right-clicked it, and because it was a static array, it already knew the bounds. It's from 0 to 11, and I can say evaluate, and I can get all the values for that array. So this is for rank 0. If I were interested in rank 1, I would have to go back and then say evaluate again, and notice how it refreshed the values for rank 2. Okay. Now, if I wanted to say I want to know what the value is for the first row of the array for all of the ranks, so I can say tables 0. Oops, table 0. Okay, so this is for my current rank, which is rank 1. But if I wanted to know across all ranks, I would just include this distributed array dimension, set it to 1. So now for each of the 4 ranks, I now have the first row of this tables array in numerical form. And I can also see it graphically if I hit visualize. So for each of the 4 different ranks, I can see visually what the values are. And if you wanted to, you can save the image too. So So not only does this work for static arrays, it also works for the dynamic arrays. So it's the same thing, just right-click the name and view array. But you can see here it doesn't know the bounds itself because it's a dynamic array. But we can just say set it to 11, and then it's the same thing. It's just now we're working with a dynamic array. Okay. Another thing you can do is you can add a watch point. So I can say right-click this, add a watch point. So what a watch point is it will trigger anytime this variable has its value changed. So if I were to hit play, right? So at the first time it got a value, so so actually it had a value of 24, and then it had a new value of 1 once it hit line 120. So actually, yeah, so you can see that it executed line 118, but as soon as it executed it went to line 20, and then it tells you, hey, this value's changed. Okay, so that's a watch point. It's gonna DDT will prompt you every time that value changes. I'm gonna set a breakpoint here, and because of my watch point is still set, I will get more notifications. Yeah, okay, so I was supposed to enable threads here, so if I go to 4 and then run, okay, hit play, hit the first breakpoint, hit continue, hit the second breakpoint. Okay, so at this point I can see that I do have my 4 open and B threads. Okay, and then I wanted to go to this breakpoint. Oh, yeah. I wanted to just stop after 1, otherwise it keeps hitting it. So let me just disable that breakpoint. Even though it's already set here, I can just uncheck it, then hit play. Okay, so now I'm at line 165. At this point, because I enabled memory debugging, I can do what's called view the current memory usage. So we can see that we don't have a whole lot of memory being used. In fact, yeah, so most of it's just like Darshan, but that's not part of our program. So after we do this allocation, essentially we're just going to request a couple megabytes be allocated in these arrays, which aren't going to be freed. So if I add a breakpoint here, pause, and then I do the current memory usage again, I can now see my allocation at line 89. And it tells me that in the numerical value that I have 100 megabytes allocated for each of the 4 rings. So, okay, so that's kind of how you would get an idea of where your memory is being allocated throughout the code, and it tells you not only how much, but actually where it was allocated. So at line 89. Okay. Yeah, so running short on time, so I'll stop this example. So this was a C code example, and I do want to go over another one. So I will make these files available to you. So this is something that has a bug in the code that you can use DDT to try and figure out why it's crashing and fix it yourself. And then I also have another memory debugging one. So first I'm just going to compile it and show you that there is a bug in the code. If I just do aprun-n4 solve.exe, it should crash. Yeah, and if you were to scroll up through this crash, you can see that the first thing it tells you is that there was a double free or corruption. Typically, when you see something like that, that's a clear sign that you've got a memory issue. So what you can do is you can edit the makefile to link against our memory debugging libraries. So I just uncomment this line, recompile it. Now I'm just going to take the line that I used to run it and put DDT-connect in front of it. So now because I compiled this with the Darshan module unloaded, I'm not going to see that Darshan thing when I first started DDT. Okay, accept. Okay, so to start off with, I'm just going to leave it on balanced with memory debugging, and then just see what it tells us. Okay, yep, so we don't see the Darshan function anymore, so we'll hit play, and then we'll get the crash, like we would expect, but this time we'll get a different error message because we turned on the memory debugging library. Okay, so all 4 ranks crashed. There's memory error detected at this location, and then we know that a previous write overwrote the reserved memory after the end of an allocation. So that doesn't tell us specifically what happens, but the key word here is that it overwrote memory after an allocation. So if we were to hit pause and then travel up the stack trace into our code, so this is the system call, and this is our code where the problem occurs, which is at a deallocate, which by itself doesn't tell us exactly what's going on. But what we can do is that we can now change, we can now enable guard pages, and then we want to say after the allocation, hit OK, and then restart our session. So now that we have the guard pages in place, we can know exactly where this improper memory access is taking place. Okay, so if you hit play, we can see now that we have an actual line number, check.fmoney line 27. So read write beyond the end of allocation. So only one array is being accessed. Okay, pause. And it's trying to access the k+1 element, where k is 10244. But if you were to hover over res, you can see that it's only supposed to have 10 to 40 elements in it. So we're clearly accessing something that we're not supposed to. In this particular example, it's because I just artificially added 100 to here. But as a programmer, if you have this type of bug, it's up to you to figure out why you have the situation you're in and to look over at all of the variables that might contribute to the crash. Okay, so those are the 2 demonstrations that I wanted to cover. So that was a C and a Fortran example, both with memory debugging turned on. So let me go back to my slides. So DDT, like I said, the Spark lines are a nice alternative to just doing printf because you can see visually what the values of variables are across all MPI ranks. Watch points allow you to stop every time a variable changes. I didn't showcase this, but there are static analysis warnings in case you have a variable that you have defined but you don't use it, or maybe you allocated an array, you never use it, so you're just wasting memory. So these are neat little things that DDT will tell you. Memory debugging, like I had shown, it'll detect if you access an array that's out of bounds. And you can also detect stale memory allocations if you got some type of memory leak, especially if you put a breakpoint near the end of the code before MPI finalized. You can see what is still allocated in memory, and then figure out, in here you can go to the line of code where that memory was allocated. So for using DDT on Theta, essentially you'd want to have to load the forge module. You have to specifically set the value for the version that you want. So in this case, it's 19.12. I do recommend unloading Exalt and Darshan before you compile, just to make things smoother. You would compile your code with O0-G for debugging flags and turning off optimizations, because like we saw in the previous example, if you don't have O0, you might not get information that you're wanting. And you can start it interactively, just DDT app run your command. I prefer that everyone use a remote client, which you're required to use --connect, which is what I have shown. If you do not want to do that, you can always SSH with X forwarding to the Theta node, and just type DDT with an ampersand on the login node. That works just the same way, provided that you have a really fast network connection. Okay, yep, so this is just me showing how I set up the remote client. And this is, so this was the exact settings that I used to enable the memory debugging libraries in your code. Okay, so that concludes the end of the pre-recorded session.